Today, let me first look at some numerical examples on dielectric heating. As I was mentioning last time, dielectric heating means using high frequency voltage across the specimen to be heated, and assuming that there is enough loss in the specimen, there will be enough heat produced. This method is used for heating insulators and other dielectric materials. Magnetic materials cannot be heated this way. For them, we use induction heating. Now, conceptually, what we are doing is we have the material to be heated sandwiched between two conducting plates, and the voltage supply is connected across the two plates. The frequency of the supply is F, the magnitude is V volts RMS, the current going through the specimen is I amperes RMS, the thickness of the material is small t, the area of cross section of the plates, assuming that plates are fully covering the material, is A. It is the area of cross section of the material that matters ultimately. So what we do is we use basic laws of AC circuit analysis to calculate the current going in. And we also remember that it's a lossy material, so current and voltage will not have perfect 90-degree phase shift between them. And that fact that current and voltage are not exactly at 90-degree phase shift between them produces the loss. So to cut the story short, let me define the various parameters. Material thickness is small t. Material's dielectric constant is epsilon r. Loss tangent is tan delta, and delta is known as loss angle, which delta is nothing but power, the phase shift between voltage and current is supposed to be phi, okay? And phi is 90-degree minus delta. That's the way it is defined. I'm writing it all down later. Now, for a lossless material, delta is 0. So tan delta is 0. That means no heat would be produced. There's no point trying to heat a lossless material. Of course, there is no lossless material in nature anyway. The material has to be lossy enough for dielectric heating to work well. That's for sure. Okay. Now, first thing you need to do is calculate the reactance of the material, which is 1 upon omega c or 1 upon 2 pi fc, where c is the capacitance. And capacitance can be written using the well-known formula epsilon naught epsilon r a by t based on this geometry. Okay. So that's what I'm doing next here. First of all, if you know the capacitance, you know the reactance, and we are talking magnitude of current and voltage. So the magnitude of current will be V divided by the reactance of the specimen. Okay. So 2 pi f CV is the magnitude of the current that would flow in this specimen. These things are simple. Now, coming to capacitance, before we do that, actually I've got things in a different order here. The power dissipated will be obviously Vi cos phi. We are talking real power. Cos phi is the power factor of the material, and cos phi and tan delta are related by, in fact, phi and delta are related by these equations. Phi equal to pi by 2 minus delta in radians, or 90 degree minus delta in degrees. And generally, delta is not very large for most practical materials. So tan delta and sin delta are almost equal to each other. So cos phi can be written as sin delta, which is approximately equal to tan delta. That's why this equation has been written. These values are given to us for a given material. And P is obviously Vi cos phi, and I is V divided by XC, and cos phi is approximately sin delta. So putting all that together, I get this equation for power dissipated in this specimen. And XC is 1 upon 2 pi FC. So I use that to come to equation 10. So the formula for power dissipated is 2 pi FC V square sin delta. And sin delta is approximately equal to tan delta, so many people use this formula, equation 12. Tan delta is given to you normally in the problem itself. Okay. Now capacitance. This is the formula we know very well for calculating the capacitance. Epsilon naught epsilon R A by T. A is the area of cross section of the material of the dielectric slab. Okay. Epsilon naught is a well-known value. At permittivity of free space, it is given by 8.854 multiplied by 10 raised to the power minus 12 farad per meter. Epsilon R is the dielectric constant, which also will be given to us. Area of cross section will be given to us. T would be given to us. So calculations are not that difficult. Now here is one numerical example, close enough to reality. A slab of insulating material, which is dielectric, 130 centimeter square in area and 1 centimeter thick, is to be heated by dielectric heating. The power required is 380 watt at 30 megahertz. Material has a relative permittivity of 5, which is relative permittivity means dielectric constant, and power factor of 0.05. Absolute permittivity epsilon naught value is given. Determine the necessary voltage. So what we do first is calculate the capacitance of the specimen or of the dielectric slab. Whatever word you want to use is okay. Epsilon naught multiplied by epsilon R multiplied by area divided by thickness of the material. And convert everything to MKS units. Otherwise, you may get a wrong result. This value of epsilon naught is in farad per meter. So area has to be in meter square. Thickness has to be also in meter. The given values are in centimeter square and centimeter. Convert them to meter square and meter. 130 multiplied by 10 raised to the power minus 4 multiplied by 10 raised to the power minus 2 for thickness. Dielectric constant is 5. They're talking about wood here. Wood has dielectric constant approximately 5, I think. Okay, so substitute all the values, calculate the capacitance. It turns out to be quite small, of course. That's why we need high frequency to produce enough current and enough heating. 57.551 picofarad is the capacitance value. Now delta is related to phi, which is also related to power factor. Power factor is 0.05, so cos phi is 0.05. So phi is cos inverse of 0.05, which gives you 87.134 degrees. So delta is 90 minus 87.134 degrees, which gives us 2.866 degrees. Tan delta is what we need in the equation for power. This equation, tan delta or sin delta, which are almost equal to each other anyway. So in this equation, tan, or if you want, you can use 12 directly. You know frequency, you know capacitance, you know power, you know tan delta. The objective is to calculate the applied voltage that would be required. P is given as 380 watts. Substitute all the values carefully. This is a reasonably complicated calculation, so be careful. The answer you get is actually V square, and you have to take square root of that. To get the voltage. Frequency is given as, I think, 30 megahertz. Yeah, 30 megahertz. So 30 into 10 raised to the power 6. Capacitance value is in picofarad. So I've taken 10 to the power 12 in the numerator. Tan delta is almost 0.05. So I substitute that. Epsilon R is also given. Epsilon R is not necessary because it's included in the capacitance already. So please double check this calculation. The required voltage turns out to be 837 volt. So you will need a transformer. The available voltage is 220 volt. You'll need a transformer to step up the voltage to this value. And the current requirement is also going to be high, although we are not calculating current. We could have done current calculation also to complete the picture. That would also tell us how thick the wires of the transformer need to be. Okay. But they are not asking us to calculate current, but it's easy. Once you know voltage divided by XC to calculate the current required. XC is 1 upon 2 pi XC. Okay. We use all these formulas. Now, second problem is even more interesting. Here they're saying a wooden board, clearly. A wooden board of dimensions 100 centimeter multiplied by 50 centimeter, that is the cross section. It's a rectangular board, and 2 centimeter is the thickness. This is, furniture application for how to use dielectric heating for making furniture long lasting. Moisture, etc. is taken out by heating it gradually. So a wooden board of dimensions 100 centimeter multiplied by 50 centimeter multiplied by 2 centimeter is to be heated from 25 degrees Celsius, which is around room temperature, to 175 degrees Celsius in 10 minutes by using dielectric heating. A 30 gigahertz supply is being used. The specific heat of wood is 0.35 calories per gram per degree Celsius. The density of wood is also given as 0.5 gram per centimeter cube. The dielectric constant of wood is 5. The power factor of wood is 0.05, like in the previous problem. How much voltage will be needed across the specimen? How much current would be drawn during heating? Assume that the loss of heat energy due to radiation, convection, etc. is 5%. So they are saying there is going to be some loss. So heat supplied should be 5% more than what theory tells you, because losses are there. Obviously, sides of the materials will be open to atmosphere, so some leakage of heat would occur. That has been estimated to be around 5%. Now, how do you handle such a problem? Capacitance is easy enough to calculate, I think. Look at the numbers. A is given and we convert it into meter square. T is given, we convert it into meters. Epsilon naught is well known. Epsilon R is also given. To calculate capacitance right away. It turns out to be 1.1 nanofarad almost. Now, the objective is to calculate the voltage required. So you need to calculate how much power will be needed to be supplied. For that, they have given a lot of information. They have told you that the specimen needs to be heated from 25 degrees Celsius to 175 degrees Celsius in 10 minutes. We assume uniform heating, uniform rate of increase of temperature. So if you can calculate the total energy required in 10 minutes, then dividing it by time of 10 minutes will give you the power required. Now, how do you calculate the energy required? I'll show you how. Calculate the volume of the specimen, which is 100 centimeter multiplied by 50 centimeter multiplied by 2 centimeter. So result is in centimeter cube. The density of the material is also given, 0.5 gram per centimeter cube per cc. So using that, you can calculate the mass of the material because volume is known. Okay. You get the mass as 5 kilogram. Now, some additional info is also there, specific heat. I think you know this. If you don't, I'll repeat the definition. Specific heat is 0.35 calories per gram per Celsius. The total energy required in terms of specific heat, mass, and temperature rise is given by this equation. This is how specific heat is defined. Total energy is mass into specific heat into temperature rise. Mass is, by the way, specific heat value is given not in MKS units, so we got to be careful here. The value given is in calories per gram per degree Celsius. So the heat calculated will also be in calories, first of all. So mass is 5,000 gram. I have to use the mass in grams here into specific heat into temperature rise in Celsius. Using this equation, I get the total energy required in calories. 262.5 multiplied by 10 to the power 3. Now I need to convert that into joules. And I checked this number. 1 kilocalorie is around 4184 joule. You can double check this number. So based on that, the energy requirement works out to 1.0983 megajoules. This calorie number can be converted to joules. Okay. Now you need to be aware that 5% loss is there. So actual number that you would supply will be 5% higher than this number. So multiply this number 1.0983 megajoule by 1.05 to get the actual heat energy input in 10 minutes. So you get 1.153215 megajoule. Now this energy is being supplied over a period of 10 minutes, which is 600 seconds. So divide this energy by 600 seconds to get the power. Heat energy required. Heat power required. 1.1532, I've approximated the number, into 10 raised to the power 6 divided by 600 gives you the wattage that would be needed. It turns out to be almost 1922 watt. Okay. Once you know all this, you go back to the equations that I have given you. This equation in particular. You should be able to calculate the voltage required because everything else is known. Here we go. Yeah, that's the equation. So V is given by this formula, square root of this. P divided by 2 pi Fc tan delta. Plug in the values, 1922, 2 pi F is 30 into 10 to the power 6. Okay, capacitance was in nanofarad. So I have brought 10 to the power 9 in the numerator because of that. Tan delta is 0.05. Capacitance is 1.10 something nanofarad. So that value is also there. Plug in all the values, take the square root carefully. Tan delta, by the way, is same as in previous problem because the same values that were given in problem 1 have been repeated in problem 2 also. So using all this, we get required voltage to be almost 429 volts. So, sorry, this is correct. Now current required will be obviously voltage divided by reactance, and reactance is 1 upon 2 pi Fc. So current required will be 2 pi Fc into V. You can double check this calculation, you get almost 89.55 amperes. This is how you tackle plywood heating. Other heating problems can be handled in a similar manner, of course. The last problem is a repetition of the previous one, assuming that frequency has changed to 10 megahertz. So you can repeat it. I have not done it myself. You can repeat the entire calculation. If frequency goes down, you'll see some interesting results. In fact, I believe that you may not have to calculate everything all over again. If you look at the formulas carefully, and you know that frequency has gone down by a factor of 3 compared to previous problem, you should be able to work out the new values directly. But anyway, I'll leave it to you. Repeat the problem for 10 megahertz. Okay. This is how we handle dielectric heating calculations. Now I want to get back to the PPT I was showing you last time. We were talking about induction heating. Let me finish it today. There's a lot of detail in induction heating or induction furnaces. Okay. They are mostly used in industry. You don't see them in homes for sure. They are used for a large variety of practical applications for processing metals and so on. I don't think I expect you to remember each and everything given in the PPT, but remember that what we are doing is we are using the induced currents to produce the heat. The material to be heated is metal generally, and that short circuits the currents that are being induced in it, and that produces the large value of heat that we need. As simple as that. Small domestic furnace. Nowadays, induction cooking is becoming popular. That is one example of domestic application of induction heating. But in general, this method is very popular in industry for sure. Annealing, hardening, gap sealing, heat shrink fitting, wire stripping, and so on. Very popular method for all those things. What are the advantages of this method of heating? Stirring is not necessary. It is natural because of the electromagnetic waves that are produced in the material. Melting is cleaner. The furnace can be installed in a very compact manner. High melting rates can be obtained even with small furnaces. Energy conservation, the efficiency is not bad at all, 55 to 75%. It is definitely better than combustion in terms of efficiency at least. Even it's in terms of cleanliness, it's better than combustion for sure. There are two different varieties in principle, core type and coreless type. Both are okay. There are advantages and disadvantages for each of them. I don't think I want to go too much into details of everything, but it's there in case you need all the info in the future. Now I want to show you the next method of electric heating, which is very popular in semiconductor industry. This is known as electron bombardment. It is virtually the same technology that you see in cathode ray oscilloscopes. The narrow pencil type of beam containing high energy electrons is used on specific areas of the semiconductor to produce the required heating or achieving certain goals in the operation. This method can be used for gas also, I suppose, but I have seen it being used for solid materials only in my life. This method is not that useful for mechanical engineering purposes, but for semiconductor people, it is very powerful. Very narrow areas of the material can be treated using this high intensity beam of electrons. You can essentially open the CRO and take the beam from there and use it. But of course, you got to be very careful not to get accidents out of it. Other method is infrared heaters. Infrared are the frequencies just below the optical frequencies. Nowadays, they are also being used a lot for electric heating. The mechanism is similar to what sun does to us in the daytime. Sun produces a lot of infrared. These rays come to us. They heat everything by using the fact that they are absorbed by the material. This is not I square R type of heating. Here the material fully absorbs. Our bodies also absorb infrared and then keep it there for a long time. Even if sun disappears, we will still feel hot enough for some time because of the absorption that has happened in our bodies. Infrared heaters are becoming very popular in buildings, especially in industry. Once they have been put on for say a few hours, enough heat will be absorbed by material around them, and even if you switch the heater, the material will continue to remain warm for a long time. Okay. The frequency, the wavelengths are given here. They are just below the optical range. Infrared heaters are available infrared oscillators are available to give you the voltage that you need or the power that you need. Okay. This could be a very interesting thing for you to pursue as a career, because right now in this country, all infrared heaters are being imported. Nobody is actually building them. You can think of having a career in this direction, how to build them in this country itself rather than importing and selling. Okay. Okay, there's a lot of detail here. Again, no, I don't expect you to know everything, but be aware that it's an oven after all. Or it's if not oven, you can call, yeah, it's oven probably. Or if not, at least it's a heater. Okay, for sure. Which will require a lot of controls besides the heating chamber itself. So that is what is shown here in this diagram. The last method of electric heating is microwave ovens. A lot of you must have seen it. The frequency used is typically 2.4 gigahertz. It is again kind of dielectric heating, because the food to be heated is lossy. It has tan delta high enough. Okay. However, current is not directly passing through the food. The generator of high frequency energy is away from the food, and through convection and radiation, the energy is getting to the food. So there's a bit of difference here compared to what we saw in plywood scales. Okay. The generator that is used to produce 2.4 gigahertz signal is known as magnetron. Again, there's a lot of detail here. You may not want to know everything, but be aware that this is also a very popular method of electric heating. Okay. So that gives you an overall idea about what is happening in the world of electric heating today. Low frequency versus high frequency is one way of looking at various methods. Indirect heating versus direct heating is another way of looking at these methods. And among each category, there are several other varieties. So keep this PPT with you. I'll also issue an assignment where I'll tell you what I expect you to know for exam. The last topic, which I will get started with, but we will finish it in the next lecture for sure. It is called electric drives. Why do we need electric drives? You know, we have seen a lot of motors, AC and DC both, and three-phase and single-phase both. A motor in industry is always seeing variable load. Torque keeps changing, RPM also keeps changing, and as a result, power requirement also keeps changing. Our objective remains to get the best efficiency from each motor in a dynamic manner. That is achieved by an additional gadget called electric drive. Actually, the word is drive. There can be mechanical drives also, which will help in improving the efficiency of a motor continuously. But electric drives are much more preferred because they give better control. So to get the best performance from electric motors is what drives do. As simple as that. What you do is, you have not been taught the course on control systems yet, but someday you will be. You will see that the purpose of a control system, which what drive is all about, the purpose of a control system is to monitor the performance of the motor and compare it with some expected performance, generate an error signal, feed it back to the input of the motor, and change something at the input so that the motor comes back to optimal state of affairs. That is the purpose. What is a drive? This is a formal definition. Any system employed for motion control in mechanical or electromechanical systems can be defined as drive. That's a formal definition. So it is not only for motors. For any electromechanical system, drives can be used. Motors are one example. Drives help in efficient, optimal, and cost-effective control of motors. Irrespective of the nature of the system, the drive can be either mechanical drive or electrical drive or electric drive. What is electric drive? It's a form of machine equipment designed to convert electrical energy into mechanical energy along with providing electrical control of the processes involved. What they are doing in this definition is they are including motor in the definition of drive itself. That's why they are not saying controlling the motor. They are saying motor is part of the drive. Fine. That's another way of looking at things. Motor is a part of the drive. In modern definitions, motor is considered to be part of the drive, rather than saying motor is being driven and controlled by drive. Okay. Now, input of the motor is either AC signal or DC signal. How much signal is going will be controlled based on how the motor is behaving. And that control is done using a semiconductor device typically called SCR, solid state rectifier, or silicon control rectifier. That's a better word, I suppose. It is also known as thyristor. It is a variable resistor whose value can be controlled based on the bias voltage applied to it. It is a semiconductor based resistance. The value depends on applied voltage to it. And of course, microprocessors are needed also. I know you probably don't understand this word too much. In the course on mechatronics, you will be taught a lot about microprocessors. But essentially, these are uh, circuits based on op amps. You have been taught op amps, operational amplifiers already. A lot of op amps are put together to process the error signal coming out from the output. And based on the processing result, the thyristor is told to do something to the input of the motor. Okay. This is not the right course to talk about microprocessors too much, but at least the word should be known to you. In fact, electric drives typically require 3 to 4 lectures, but I'm going to be finishing it in one lecture almost, okay, for the sake of completing everything in time. Now, conceptually, the electric drive has these components. Source, which is the AC input or DC input, depending on the nature of the motor. Power modulator, that means how much of the source voltage is actually going to the motor. Not only magnitude, even frequency can be changed if necessary. Even phase shift can be changed if necessary. So power modulator does that. It modulates the output of the source in a desired fashion before feeding it to the motor. The output of the motor, of course, is connected to load. But suppose motor is not able to perform at its optimal, then a sensing unit will tell us that. It will generate a signal that goes to control unit, which has a lot of microprocessors inside. And that control unit will continuously talk to power modulator saying, do this to the source, do that to the source. And control unit has an extra input, which is manually controlled. It is called input command, which can be used if you want to do something drastic. Like if the motor is not behaving well at all and the loop is not able to correct the motor's behavior, then you may want to intervene manually. Even full stoppage of motor may be necessary to correct the situation. For all that, an extra input command is available to the operator, which can override everything else and will tell the motor to stop, or will tell the input source to stop, or whatever. There's so many options available to the operator. So input command remains the ultimate solution if nothing else is working. But no, we normally don't want to use the manual input. If the self-correcting loop is well designed, it will continue to correct the motor's performance in a dynamic manner. Each of them has a law circuit diagram inside, excepting motor, which you know very well. Control unit has a big circuit diagram. Sensing unit also has a reasonably big diagram. And power modulator also, not a big diagram, but some diagram is there. And source, of course, is another story. It comes directly from the AC or DC supply that is available in the factory itself. This is a conceptual diagram of an electric drive. I'll stop after this. We have got solar panels on the left side, which are producing DC voltage. Okay. And solar panels can store energy during the day, and you can use that energy in a 24-hour manner. Assuming that panels are large enough and the number of panels is also large. The DC voltage is converted to AC voltage by using inverter, assuming that we are dealing with an AC motor. If you were using a DC motor, this inverter will not be necessary. And then the electric motor is feeding the load. The load is shown on the right hand side. It's a conceptual diagram. The actual load is not shown, but we have drawn two cylinders on top and two at the bottom and a shaft in between to show the mechanical load. Okay. Now this is unfortunately missing the control loop. So motor will behave in a particular manner over which you have no control. This is an electric drive which is open. And this is another illustration where the drive is mounted on top of the motor. The drives are there on the top on both motors. These are two cascaded motors, and each one has a separate drive on it. And I'm assuming that they are automatic control because I don't see any manual input or anything.